In this module, we're going to introduce the magnetic flux density, which is denoted by the letter B. This is kind of the equivalent of the electric flux density, which is denoted by the letter D. And we'll also finally to wrap up and look back at tying it to earlier concepts, we're going to compare the magnetic field concepts we've learned so far with the electric field concepts that we've covered, just to see what kind of connections we can make. So we're going to introduce the magnetic flux density and then also relate B and H to D and E conceptually. So as you can imagine, in a way, as you can relate the electric fields to the electric flux density, you can similarly come up with the concept where if you have a magnetic field, you can normalize the field lines to the area and come up with a magnetic flux density, which takes into account, and then when you connect the two, you take into account the material characteristics. So in this case, very similar to how the electric flux density is equal to epsilon E, the magnetic flux density is going to be equal to mu, the permeability, times the magnetic field H, and it will have the units of Weber per meter squared, or in this case, this particular quantity also has the unit of Tesla. Now this mu quantity is the permeability, which is the equivalent of permittivity, but for magnetic fields, and we have the same notation where the permeability, we have mu naught, which is the permeability of a vacuum. And if it's not a vacuum, you can often relate the permeability to a vacuum through a unitless quantity mu r. So this would be the relative permeability. And this quantity here, the permeability of a vacuum, is another universal constant. It is nicely 4 pi 10 to the minus 7 henries per meter. Now with this quantity armed in mind, you can also imagine, that we now have this quantity of magnetic flux density. Therefore, you can also define the magnetic flux, which would simply be the density integrated over the area. Right? So magnetic flux would be equal to B dot ds. In this case, when we do magnetic flux, when you do the electric flux density, do we have the equivalent of this value? Remember why don't we have a symbol for the electric flux density? What does d dot ds end up being equal to? Right, the total amount of electric flux is actually a quantity we know. In this case, in the case of electric fields, it also happens to be equal to the total charge. And so that's why we don't have a nice fancy-looking Greek symbol for electric fields, because in the case of electric flux, the total amount of electric flux equals the charge enclosed, so we just call it the charge. Now, in case of magnetic flux, you can imagine that the total amount of magnetic flux in a closed surface, so if this was a closed surface, it would be equal to the magnetic charge enclosed, right? But what is a magnetic charge? It would be a magnetic monopole, right? So if you had a magnet bar and there's a north and a south, it would be the equivalent of just having this north part, right? Which we have not been able to find yet. So since nobody has thus far been able to discover a magnetic monopole, the closed surface integral of B dot ds is always going to be equal to 0. So that is a key fact to keep in mind. Whereas the closed surface integral of d dot ds is going to be equal to q, the closed surface integral of the magnetic flux density is always going to be equal to 0. If you can prove otherwise, then I'm sure there is a great big career prize awaiting for you at the end of that. Now, if we shrink this, remember what the differential form of this is? The differential form of a closed surface integral? That's right, it's the divergence. Right? So if you take it into point form, the equivalent of that is saying that the divergence of B is always going to be equal to 0. And that is that is a key fact that will be one of Maxwell's equations that will, when we tie everything together. Now, remember, for electric fields, we also had, for magnetic fields, we introduced the curl, right? So what is the curl of an electric field? So what is the equivalent of curl of E? Well, remember, curl is the shrinking down of a clothesline integral into point form, right? So if you take a clothesline integral and shrink it down into point form, you get the curl of E. And what's the clothesline integral of E dot dl? This is our equivalent of Kirchhoff's voltage law, right? Since an electric field is always conservative, if you take a closed loop integral, you will end up where you began with potential energy-wise. And so closed loop integral is always going to be equal to 0, which means that curl of E in electrostatic fields is always going to be equal to 0. Note that we're referring specifically to electrostatic fields. For completeness, I should also say electrostatic and magnetostatic. So note that we don't really have any time-varying fields for the moment, and so while those criteria are held, we have no monopole charges, so the divergence of B is equal to 0, and the curl of E is going to be equal to 0. Let's wrap up by doing an electric magnetic field comparison of everything that we've done so far, and that will also map out some concepts that we'll be looking at in the future. So I'll start with the electric field. We're going to look at also the magnetic field equivalent. So we have the differential form of some person's law. In the case of electric field, it's going to be Gauss's law, where the divergence of D is going to be rho v. And also, we just learned that the curl of E is going to be equal to 0. In the case of magnetic fields, we have the divergence of B is always going to be equal to 0, and the curl of H, which we learned previously, is going to be equal to the current density. Right? Next, we'll also have the integral form. So the integral form of these, which was what we learned a little bit earlier, is that a closed surface integral of D is going to give you the Q inside. The equivalent for magnetic fields is that the closed surface integral is going to be equal to what? 0, right? And then line integral, if you do a closed line integral in the case of electric fields, you get 0. In the case of electrostatic and magnetostatic fields. And in the case of magnetic fields, if you do a closed line integral, you're going to get what? You're going to get the current, right? The integral form of J. We also looked at the flux density. So the relationship between the actual field versus the density of the field lines, which is related to the materials. The electric flux density is going to be related to the electric field through epsilon. The magnetic flux density is going to be related to the magnetic field through mu. Mu, in general, like with all things magnetic fields being a little bit more complicated than electric fields, mu is a different can of worms, so just throw that out there. It's not necessarily, in most cases, as simple as epsilon, but for the purposes of this class, the main thing that we just want to know for now is that the magnetic field is related to the magnetic flux density through mu, just like in epsilon. In the case of potential, since the electric field is conservative, we have the concept of potential, which we relate to the electric field through the gradient function, and we also have the Laplacian or Poisson's equation, where the Laplacian of V is going to be equal to minus rho v over epsilon. In the case of magnetic fields, we have the concept of vector potentials, which for the time being is a little bit trickier, again, because the magnetic field in its basic form is not conservative, and so it's a little bit more complicated, and we're just going to keep it out of scope for this class. And we also have some related theorems, right, when we relate the two. In the case of the electric field, we introduce the trick of the divergence theorem, which says that if you have a closed surface integral that you don't want to do, you can also take the divergence of that vector field and do a volume integral instead. In the case of magnetic fields, we have Stoke's theorem, which is if you want to weasel your way out of doing a line integral, a closed line integral, what you can do instead is to take the curl of that vector field and then do a surface integral instead. Again, if it's a closed line integral, that means it forms a surface. So then you can just take the curl and do a surface integral instead. Another thing that we haven't covered yet, but let's just throw this out there so you have a framework for the concept when you learn it, is the boundary conditions. Right? So in the case of electric fields, the tangential field component is going to be continuous. So that means E1 parallel is going to be equal to E2 parallel. And then the normal component, D1 minus D2, is going to be equal to the surface charge density. Right? So D1 perpendicular is going to be equal to minus D2 perpendicular is going to be equal to rho s. And this is fill in later. So I encourage you to check back to this table, this framework, and keep an ear out for when you learn the equivalent for here and fill that out in your own notes. And then separately, we have stored energy. Right? In the case of electric field, it's going to be equal to 1/2 the volume integral of epsilon E squared dV. And you can imagine that there is going to be something similar for the stored magnetic energy, which if you look at this equation here, you can probably guess what it's going to look like, but for now it will be in the fill in later category. So there you have it, the first significant part of our magnetic field journey.